the kind of problem that no one seems to want to talk about is like, if I'm an L2 user, like the whole reason why I'm on L2 is because I don't want to incur L1 costs. Mm-hmm. If we're only willing to take on the trust assumptions of these bridges, then the user will always incur L1 costs. The user experience of that is completely untenable. Our solution to this is economic security.
Hi, I'm Shane Barrett. I'm a research partner at Hack VC, and I'm here with York, who's one of the founders of Hyperlane.
Hey Shane, thanks for having me.
So let's get started. What is Hyperlane?
Yeah, thanks for inviting me on. Hyperlane is an interoperability protocol that is implemented entirely in smart contracts, which, for those who don't know, has become kind of a shelling point for developer ecosystems in different blockchain communities. And so that was kind of a conscious choice for us to implement it entirely in smart contracts to make the API to the interoperability protocol kind of the most accessible and available to all these different developer ecosystems, as opposed to kind of having it be enshrined in the chain stack and requiring a hard fork in a chain to basically adopt Hyperlane as like the validators opting into some new client upgrade. So we've been around for 2.5 years, or in production for about 2.5 years. The history is kind of interesting. We share a common ancestor with the Nomad protocol in terms of code base and kind of design philosophy. If folks are familiar with Nomad, which was what we call an optimistic interoperability system. But interoperability in the context of blockchains is basically bringing the composability that everyone kind of lauds blockchains like Ethereum as like enabling this new DeFi ecosystem, or this new kind of ecosystem of applications, decentralized applications, to exist. That's possible because of composability on these smart contract blockchains. And interoperability just means bringing composability between applications that are on different chains. And so the lowest level interface that developers have in Hyperlane is what we call a message passing interface, which is, like I said, just a smart contract. So I can kind of illustrate that.
Please.
Cool, so in Hyperlane, we call that the mailbox. And you're gonna have to excuse my bad handwriting, but we call it the mailbox. And so there's a mailbox on both chains. So you can over here.
So this is one chain and this is another chain.
Yep, you can think of this as the chain boundary. And these are both smart contracts that exist on different chains. And so an application which exists on chain A makes a smart contract call to the mailbox, and there's 3 parameters to that message passing interface. So the first parameter is the destination chain. Mm-hmm. So if this is chain B, then the first parameter is basically going to be B. Mm-hmm. The second parameter is the destination, or the recipient contract on chain B.
Okay, so the address.
Correct. So there's some recipient over here. So we're going to call that recipient. And then finally, actually, the payload, or the body of the message.
Mm-hmm. Which can be anything.
Which can be arbitrary bytes.
Yeah, arbitrary bytes. Okay.
What gets actually passed over the wire includes some additional system headers, which are required for a few properties that are desirable for applications. So one is what we call replay protection. So we want to ensure a once and only once semantic for this interface, such that this message that this application sends, if there's one function call that they've made here with this set of parameters, that message only gets delivered to the recipient once and only once.
Mm-hmm. So do you want to maybe detail the message headers here?
Yeah. So I guess on the headers basically include a nonce.
Mm-hmm.
It's the sender, so I can call this S. The sender.
Sender address.
Yep. The recipient.
Which is already in the original message.
Correct. The destination, which is also in the set of parameters that the application passes.
Mm-hmm.
The origin. And there's actually a version, which is not really important for,
Mm-hmm.
and then the body itself. So we basically, to guarantee replay protection, we basically derive a kind of like globally unique identifier. We call the message ID, which is just the catch hash of the hash as like packed encoding of this. And we have some state in the mailbox on the destination chain that basically prevents an ID from being processed multiple times.
So every time an ID comes in, it checks that against its set.
Against the storage in the mapping that basically says, if I already processed this, just revert.
Mm-hmm. So I can send the exact same message, but just alter one byte in the body, and that could still go through.
Correct. And another important piece to understand is this nonce. So we want to allow an application to send the same parameters. We just want to guarantee the semantic of once and only once per call.
Mm-hmm.
And so the origins, the nonce is in the storage of the mailbox in the origin chain.
Okay.
And it's monotonically increasing it's incrementing for every message that is sent.
Okay.
So
It's global across all applications that are calling you
all applications on this chain.
on this chain. Okay.
So each mailbox has its own nonce, and by that being one of the kind of inputs to this identifier derivation, in addition to all of these other basically domain separators, we can guarantee global uniqueness of the message identifier.
Mm-hmm. So it wouldn't make sense for all chain Bs to store the nonce counts of all chain As, which is why you ended up with this hash design.
That is one reason. It would be it's just inefficient, basically. But you could try to do that, but one of the key properties of Hyperlane is what we call modular security, which is actually allowing the message recipient over here to specify their own security constraints, which basically means how can this application be confident that this message was actually sent?
Okay, so should we dive into that a little bit more?
Yeah.
So once the mailbox is called, the mailbox then has been called with that message. And obviously chain A has no access to be able to send a transaction on chain B. So how does actually all of this content end up here?
Yeah, great question. So it's a great call out. There's no ability for this smart contract to initiate a transaction on this chain because obviously the smart contract is not networked outside of the execution of its VM. So we need some off-chain actor to basically bring evidence of this message being dispatched on chain A. And ideally that actor is not trusted. So, or at least it's trust minimized, or we have some sort of crypto-economic security associated with that actor. So in our system, we call that the relayer. So the relayer is basically indexing these messages as they're dispatched to this mailbox and
have been confirmed in some sense.
Correct. Although we actually kind of the finality is part of actually different recipient applications could basically constrain the finality differently.
Mm-hmm.
But so the relayer, because it's not a trusted party, is not really prescribing a kind of preference on finality. But let's just say that they're using like whatever. Like the reason why the relayer would care about finality is because they're charging a fee for this service they're providing. But I'll get into that in a second. So they're indexing the messages that are dispatched on every mailbox contract, and they look at the destination, and they say, okay, I know what the mailbox address is on that chain, and there is a function on the destination chain called process, which anyone can call. It's permissionless. That basically requires you to pass in two parameters. So one is this entire message, so including the headers. And the other is what we call the proof metadata. And this is basically a something that anyone can observe just by indexing the origin chain, and that's where the relayer is getting that from. But in order to come up with this parameter, the relayer needs to look at the constraints that the recipient application has specified for its security. So we call that concept Interchain security modules. And there's basically a smart contract interface. In the same way that there's a smart contract interface over here for the message passing, there's a smart contract interface for recipient applications to specify their security requirements. So they can basically configure a smart contract that has a function on it called verify. This is the Interchain security module, ISM. And that takes in these same parameters, the message and the metadata. And this can have an arbitrary implementation. We have, at this point, more than 10 different kind of like ISM implementations that applications can use off the shelf, but ultimately they can implement whatever they want in this function.
And it returns yes or no, basically.
Returns a Boolean.
Okay.
So the way the mailbox works is before it will actually deliver this message to the recipient, it will ensure that the ISM returns true for a given message and metadata.
So it looks up the recipient, checks what the ISM is.
Exactly.
Calls the ISM.
Exactly.
Checks that it's true, then calls the recipient.
Exactly right. Before it calls the recipient, it does the replay protection mapping I mentioned earlier, just for like reentrancy protection. But that's the gist of it. And what gets passed to the recipient is actually just the origin and the sender and the body. So the recipient doesn't really need to know about these headers. Or kind of like the mirror of that, so that's the lowest level interface that applications have as kind of like part of their smart contract interface. But let's get into this kind of like off-chain infrastructure a little bit, because the smart contracts, like at least at the lowest level, are fairly, I think, simple to understand. We can also dig into different flavors of ISM and kind of why there would be a need for you to have this be configurable as opposed to just having some global security module that every application is opted into. So maybe let's start here and then we can get to that. Okay. So, like we said earlier, the relayer is an off-chain agent that is basically programmed to understand how to process messages and produce proof metadata, which actually will verify is true. But we don't want to, or like the relayer needs some way to ensure that it's not just there's not a freeloader problem, right? You don't want to require that every application has to run their own relayer, because then you're not really providing a super useful developer tool. This is like classic cloud services, like SaaS style. You want SaaS style guarantees when you use the developer tool. You don't want to like have to host everything yourself. That's like the direction we've been moving in for the past decade or so.
And the relayer is the one who ultimately has to pay the fees on chain B. Right?
That's exactly right. Yeah. So the transaction that they initiate to do this process call obviously costs them money, and there's a few dimensions to that cost basis. So one is obviously, or like we probably all know that like transactions are cost like the gas times the gas price. That's consistent across most smart contract VMs. There are some that have slightly different cost models, but for simplicity, let's just say this is the function. The gas is actually not necessarily known at dispatch time, because the recipient, when they receive this message, can go do arbitrary computation over here. Let's say it's some DeFi swap, or we don't know if like there's a liquidation or whatever is going to happen over there. So
it's just anything could happen.
Anything could happen, exactly. And again, that's like if we want the composability magic of smart contracts to kind of transcend chain boundaries, like that is a necessary property that we can support arbitrary like execution on the other end. So this is not necessarily known at dispatch time, but in the same way that users on a front end bid a certain gas limit based on like a gas estimate that they have like benchmarked through some kind of off-chain call, we have a similar API. So the application sender, there's like a default gas that covers a lot of simple use cases, but there's basically an additional parameter that the application sender can specify, which is basically like a gas limit.
Okay, so it could be, say, 400,000.
Exactly. Okay. And the relayer basically needs this information to decide whether or not the requester has like covered or the message processing is kind of has an expected result based on what the application requests. Why do they care about that? Again, because there's like a payment associated with that. I'm getting there. So yeah, the gas is the first part. The gas price is the second part. This is also not known at dispatch time. Yes. Or at least, every application doesn't necessarily know this.
Yeah, you don't want this side to have to know what the gas price is on GMB necessarily.
Correct. And there's even a third dimension to this, which is kind of like implicit, which is actually asset price. Because in many cases, the asset that a chain is charging for fees over here is different from the asset that the origin chain is charging. So let's say this is ETH and this is Matic or on Polygon or something like that. So the relayer actually has to, their cost basis is denominated in potentially a different asset than the chain that they're being paid on.
Relayer has an account over here and an account over here, and has to basically pay over here and be paid over here.
Exactly. So they're taking on some like you can think of it as like a forex risk, and there's a few different kind of like models we have for the relayers for how they can kind of manage that risk. So one is they can oracleize the gas prices and asset prices on the origin chain and give a guarantee at dispatch time to applications that they will honor whatever the Oracle price was reporting.
Yes.
Cool, yeah. So there's an Oracle model where basically the relayer can commit or can provide an SLA basically to the sending application on the origin chain, saying like, hey, whatever prices that I'm oracleizing on the origin chain, I will honor, even if those have moved once I'm actually processing your message on the destination chain, I will just kind of honor those prices that I reported to you. And this is useful because this composes well with end applications. So oftentimes there may actually be, in the same way that there's arbitrary applications over here, there can be arbitrary applications above this one, which is sending the message. And then there's a front end up here somewhere where a user is signing a transaction.
Mm-hmm.
And
the user has to be charged something.
The user has to be charged something exactly, and they have to, they have to be able to estimate gas, to know how much they have to pay, and all that sort of thing. So if we don't do this kind of like at dispatch time, kind of like quote, you can think of it as, for what it's going to cost on the destination chain, then
someone's going to eat that. Basically.
We need some escrow, basically, which is another model that we support. But what we found is that because of the composability benefits of this, that most applications prefer this.
If you escrow, you have to talk back from chain B back to chain A.
Exactly. So that's the other model, which is basically what we call it contingent interchain gas payments. The system I'm describing is we call it interchain gas. It's just a funny name, but yeah, the other model is basically there's an escrow. Kind of think of it as like a bounty. You can actually like apply kind of some cool like auction like parameters if you want to make the market for relaying competitive. But long story short, like there's a bounty and a relayer must come back to present a receipt of what they delivered. This is actually how IBC works. That there's like a receipt that's delivered back to the origin chain, like an app. There's a lot of downsides to that model. So
we get into what you do most commonly.
This is the most common model basically that we're oracleizing, and each relayer can kind of tune these Oracle prices based on their risk, right? So they're taking on this 4x risk, and let's say that an application is like perfectly requesting the gas limit that they know will be used on the destination chain. So kind of ignoring that that's like a dynamic parameter. The relayer can choose to basically include a margin in the prices that they're oracleizing to account for this 4x risk. And we don't prescribe any like floors or ceilings on that. We run our own relayer, and we kind of have a trade-off of like, okay, well, it costs us this amount to actually update the oracles on like whatever frequency, and here's the exchange rate volatility. There's kind of a bunch of things that go into our model, but anyone can run this relayer service. If you want, you could turn off the gas enforcement policy entirely, and we have tooling that for people that do that and get up and running quickly if they're just trying to like prototype basically, or get something running on like a new chain that they're launching where they don't care so much about the economics. They're just trying to like get to an end-to-end demo, and so all this stuff is configurable, and definitely like
What makes it modular?
Yeah, I want to emphasize, I guess, that none of this is enshrined, right? This is all kind of like, you can think of it as like a SaaS style SLA of like, this is what our relayer does. People can compete with our relayer. And the applications can always choose to route to a different relayer. That's basically just another parameter that they can specify here. Either the bounty system, where there would be a competition for kind of a race to present a receipt of process,
But by default, there's one relayer that you're using.
By default, there's what we call there's a hook on the mailbox that includes the IGP, which is the Interchain gas payment system, and that specifies this relayer and its Oracle exchange rates. But basically, applications can route to their own hooks. So hooks is like a Uniswap terminology.
Function.
Yeah, exactly. we just like to borrow that, but exactly, it's just another function.
So by default, not everyone can call this function.
Anyone can call this. So on this chain, there's no access control on this function.
Okay.
But by default, when applications call the mailbox on the origin chain, they are opting into a specific hook configuration.
Okay.
We call it the default hook. Like I said, that is overridable. It's just another parameter. But most applications don't want to think about the off-chain stuff, especially smart contract developers. They just want to call a function and pay for something to happen. They don't want to run infrastructure, and so for a majority of our users, this is the preferred model. But we do have some applications who are running their own relayer and are charging an application-specific kind of relayer quote. But yeah, I'm not going to focus on that today. I think the next most interesting thing to get into is how the relayer is able to come up with this metadata to satisfy ISMs.
Yeah.
So yeah, we can erase
Just this.
Yeah, sure. Let's erase that side. Sweet. And yeah, use that too. Cool. Okay. So, so first of all, let's just zoom out for a sec. The reason why you want to have modular security, as we call it, is because, well, there's many reasons, but the first reason is what we call accessibility, which is very underrated in crypto, in our opinion. But if there is some global security model, think of analogous to Formal, where there's a set of guardians that are super institutional and whatever. If I am a researcher and I have released the latest and greatest consensus hot stuff variant or whatever, and I'm trying to get to market with that innovation, I can spin up a new chain. Maybe I spin up a new L2 with a sequencer or something. I don't know, but in order for me to tap into existing network effects on other blockchains with existing applications, I need interop. And I would basically have to convince this enshrined set of operators to come and operate for my chain. And that's a really hard sell. And I think just for those who know, the price on that is very high because a lot of times these operators are necessarily institutional, right? They're you can think of them almost as custodians on a lot of the existing kind of fat head of activity, and there's no reason for them to take on that additional risk. And so you need a security model which adjusts the security budget with kind of how much value is at risk, basically. So, this recipient application that we're talking about right here, when they're just launching and they're a new chain, there's basically zero value in that contract, and so there's no reason for them to pay, $1 million a year for some validator set to kind of opt into their chain because the downside risk is zero.
Or if it's a testnet.
Or if it's a testnet, exactly. That's an even better example because that's more realistic. A lot of people are just trying to get something working end to end. And so, yeah, you want to be able to kind of hot swap your security models. That's one reason. Another reason is there's many dimensions to the security trade-offs. So I think I'll just like enumerate that. But latency is like kind of a liveness metric. We have safety, right? You can think of this as like, BOR risk. There's kind of a lot of, this is a very nuanced topic, especially in interop, because a lot of chains, people debate when transactions are finalized in order to get selecting messages, right? But the definition of finality for a lot of chains is a gray area, and that's another reason why you want to allow people to express their preference on a spectrum of risk. And so in the same way that your wallet is just hitting the sequencer RPC and not waiting for L1 finality when you interact with Base or Optimism or Arbitrum, you want to allow applications to basically choose that preference, which makes sense for their user experience. And so that's another big reason. But I think this is the big one. And I think for a lot of years, this is also, I think, underrated.
And what do you mean by latency?
Yeah, great question. So specifically, my definition is time from dispatch to time to delivery.
Okay.
And I think this is also underrated in crypto at large, outside even interop, but specifically for any type of consumer grade experience, point of sale style, buy something in a shop or whatever. This is so important. And a lot of times we get caught up in the theoretical guarantees that we can provide to kind of the largest, highest risk applications. But a majority of people in the world do not care about that, right? They're using a credit card, which has billions of dollars of fraud every year, whatever. So they just want to be able to buy their coffee. They just want to click the button on the UI and have a check mark that tells them their action went through pretty much instantly.
Even though it really takes months.
Exactly. Exactly. And ACH and whatever is on the back end's happening with the banks rebalancing. And they just want to be insured against that risk. That's a reality. And so they are willing to pay for that premium, basically. And that's, think of Shopify, think of Square, think of Plaid, all of these SaaS services exist to basically provide speed on top of those legacy rails that maybe are built for higher risk transactions. Mm-hmm. So so latency in interop, for whatever reason, there was a lot of maximalism for a few years about this, where, I think really the reality, and I don't want to disparage anyone, the reality is that interop has seen it's been the largest source of user funds lost in crypto, I think. I don't know the latest numbers, but it's over $1 billion, which is pretty insane. And
so that's getting down to here.
Yeah, sorry. So I could enumerate the list of hacks that have happened, but a lot of them have actually been in a third category, which is basically code bugs, which obviously falls into this parent category, but it's kind of you can't really analyze this in the same way. But yeah, long story short, there's been a ton of hacks, and so everyone has been very maximalist about the risks that they're taking on in bridges. And kind of people debate this all over Twitter, but everyone's okay, the only thing that'll ever work is maximally sound, a full consensus ZK client. It has to be ZK because you can't actually all of these chains that we're talking about here, the light client spec cannot be verified in smart contracts. It's far too expensive. And so it has to be ZK for this distinctness property. So everyone's okay, ZK light clients everywhere, that's the only thing that'll ever work, and let's just build towards that. And like, I think that's really a noble pursuit, but ultimately there are fundamental limits to that. One is this, that the proving times for these things are not very quick, and I would say not consumer grade yet. The other is that oftentimes a chain's like client spec doesn't generalize. So in the same way that we've embraced this like smart contract VM approach rather than like an enshrined approach, because that's a Schelling point for applications.
It's also future proof. So if things go towards ZK, you guys can tap into that here.
Exactly.
So should we get more into ISMs, what they actually are?
Yeah, sorry, I'm kind of getting my way there.
Nice segue.
Yeah, so ISMs are basically a way for you to express this spectrum of risk.
Yes.
And we have a bunch of different flavors, but the one that's most commonly used we call multisig. This is a term that people dislike in crypto.
So maybe you can repeat the function signature.
Message. Metadata.
So message we've covered.
Message we've
basically gets into what is metadata.
Yeah. So if you prefer to label this like threshold signature, that also works. That's basically what it's doing. But what we're verifying in the multisig ISM is that a quorum of pre-configured validators have basically attested that a given message was dispatched on the origin chain.
So let's say there are 10 validators.
So there's 10 validators. So we basically have
10 private
10
keys.
signatures that are passed in metadata. And
or 7 of 10 or whatever.
exactly, there's a K of N configuration. Actually, what I want to get to is actually like what we call a weighted multisig, which is something that is going live right now. But this is like the simple implementation. You have 10 signatures provided in the metadata. The relayer, when it sees a multisig ISM configured on the recipient, knows how to do the off-chain lookup to these validator signatures and basically aggregate them.
So does it communicate and ask them for the signature? Or
Good
how does
question.
that work?
Good question. So in our system, the validators are not doing consensus because we ultimately want to inherit the consensus of the underlying chains that our protocol is implemented on. And introducing an additional consensus on top just incurs latency. And so what we're actually doing is these validators are posting their signatures to a DA layer that the origin chain is sharing, basically.
So the validators see the messages also themselves, separate or along with the relayer.
Exactly.
Make their signature, post it to the DA.
Exactly.
And that's accessed by the relayer, aggregated, and then set.
Exactly.
Okay.
Thank you for spelling that out. And yeah, I think the first question that people have about this system is, okay, we talked about the relayer's incentives. What are the validator's incentives? Can the validators just lie about the contents of a message and commit fraud and process any message they want?
Mint an asset over here that shouldn't have been minted.
Exactly.
Okay.
So our solution to that is what we call like a modular proof of stake system. So those validators are posting their signatures on the DA, and on the origin chain, we have a fraud proofs protocol that compares these signatures to basically the state commitment that was made in the mailbox. So I think we erased it, but earlier, the dispatch happens, there's some state commitment that happens, the nonce get incremented, whatever. There's actually like a Merkle tree, and we call it, it's an incremental Merkle tree, which is just a gas optimization, but there's basically a vector commitment to all outbound messages that are dispatched from a given mailbox. That's what the validators are attesting to, the root of that vector commitment.
Yep.
And
You can provide a proof that it
you can provide a proof
had been sent at some time in the past.
based on the origin chain. You can provide a proof saying this message ID was or was not dispatched at a given height. And we can compare a validator signature to this proof and basically decide whether or not a validator has produced a fraudulent signature.
So if the chain forks, so if they provide the signature, then the chain forks, that would be considered a fraudulent signature.
Exactly.
Okay.
Exactly. And so that's where we get into this reorg risk question, right? So it's actually a very good question because different applications might care about this more or less. Because if so reorg risk really is about like the value in flight at any given time, because you can basically just imagine that all of that value in flight can basically be double spent on the destination chain because of those fraudulent signatures you alluded to. And so we would like to allow applications to insure against that risk. And the way we do that is we have a proof of stake system. I know I'm getting kind of far on the whiteboard here. We have a proof of stake system on the origin chain where the validators are staked. And we use this fraud proofs mechanism to decide when to slash those validators. And the slashed funds basically function as an insurance on the value at risk.
And so this isn't its own chain. This is just a smart contract on chain.
Exactly.
Okay.
And again, that is we think that is very important for a few reasons. One is if we put this on its own chain, we are no longer inheriting the consensus properties of the origin chain. And so instead of having this be kind of like an objective fraud criteria, you now are introducing kind of like a social input to, like, basically you could, if this was its own chain, you could imagine that the validator set of that chain could just censor slash messages and or like slash transactions, and
it's kind of a single point of failure. If you have 50 chains,
exactly
all around one POS.
Single point of failure, introduces latency, does not really scale. There's actually there's throughput concerns. What's nice about our model is because it's point to point, there's no kind of like overlapping load.
Yeah.
So yeah, that's exactly right. We're basically, and again, it leans into this smart contracts like maximalism. It's future proof to all these different VMs. We don't actually have to implement a custom POS for each chain's consensus because it's just a smart contract we deployed. And what's nice about this system is a given application can scale this up and down based on what they put in the multi-sig configuration.
And the amount that has to be staked.
Exactly. So we can basically create these application-specific ISMs. We're actually doing this in production with a lot of the LST and LRT asset issuers. And this basically allows them to have confidence that they have some amount of sovereignty on their token bridging solutions, so that they can issue so like Renzo is an example, we're working with a bunch of teams on this as well. And, they can basically have confidence that there is no kind of exogenous incentives because they have a validator set configuration, which is staking some percentage of their asset on Ethereum, where the staking derivative is actually issued natively, where they can use that to secure kind of synthetic issuance on L2s.
Because if it's slashed there,
yeah,
it's okay. It exists over here now.
Exactly. So there's some users which will be basically like defrauded by this faulty mint. Yep. And the slash will occur over here. Again, this is also permissionless. Anyone can call this. The relayer client we have implemented basically does this as kind of like a public good, but you can introduce incentives on top if you want. But yeah, basically the recipient application will be able to use these funds as an insurance pool for the defrauded users. And so the kind of financial question becomes, how do you manage that risk exposure?
Mm-hmm.
And we're still in the early days of basically figuring out, okay, with the value at risk, what do we need, or like with the value in flight at risk at any given point in time, how much do we need in the proof of stake system? Luckily, with ABSs and Eigenlayer and Symbiotic, there's an abundance of cheap economic security right now. So we're very over collateralized. But slashing is not actually enabled on a lot of those systems. And so like the degree to which that is actually going to pay out as insurance is still kind of unclear, but we have basically implemented our own system outside of those protocols that implements this fraud proof mechanism, and we're just basically kind of gluing together their protocols for the cheap source of economic security, but all of the fraud proofs and everything look the same. And so, yeah, we don't really have to worry so much about this, but we're basically collaborating with the asset issuers and kind of a bunch of risk management companies in the space who kind of economically model these types of like multi-asset markets to come up with what the right collateral ratios are. Like this is kind of like a treasury management problem. But yeah, I think the most interesting part of this is that I don't know if I like fully illustrated, but let's say this is Renzo, and this is in production today. Their ISM that they have configured is not a set that we have configured or recruited. It's a set of validators that are already aligned to their application and have some existing incentives within their protocol. So there's this, Luga nodes, they have a bunch of different operators who already are participating in their staking derivative native operation, who are now running this simple Hyperlane validator, which is
multi-sig validator.
Yeah, so the validator client is basically the agent that posts these signatures, and then the relayer fetches those, aggregates those, and then posts them to the ISM, the multi-sig ISM on the destination.
And they have money at stake in the POS.
Exactly. And not only do they have money at stake, but the asset that is staked does not have a foreign exchange risk with the application asset that is being minted. And so you don't need to worry so much about, it's almost like a liquidation risk where you can think about, like, because there's no exchange rate risk, it's very simple to model, okay, I have, 100 amount of like easy ETH that are going to be minted right now. I know discretely how much easy ETH are in the POS, let's say 200. And so I have strong guarantees that this is actually insured. And this I think is probably our most novel innovation. And this is very important for DeFi because it moves us from a world where we are reasoning about interop risk or bridge risk in a abstract way to a discrete way. Because now we have a way to actually economically and discretely model this risk. Whereas previously with either with just like third-party validator bridges, like Formal, right? There's no way to actually discretely model the risk that you're taking on, the counterparty risk of your application just deferring to this like global set of guardians. I guess the conclusion is just that we have a way to discretely model the bridge risk economically, which allows us to allows protocol designers to have stronger assumptions in the design state of their assets. Exactly, which we have never had before. So I think that's kind of like the critical piece to take away from this.
So I guess to finish off, maybe we can talk about like the composability of ISMs, because this is not the only option.
Exactly.
Okay.
Very true. Yes. So another reason why we built this modular security framework is we saw in the market that there were all of these different competing ideas about what the end game bridge architecture looks like. I think people are probably most familiar with this in like the L2 wars, I guess, with like, Validiums and ZK versus optimistic, and you should think of rollups just as a very specific application of bridges. They're kind of a subset of bridging. And as an application developer, if you want to reach the widest possible audience, like I experienced this myself in previous projects, but as a smart contract developer, when you are deploying to all these different L2s to like make your protocol available for users who might have a specific preference on that to use that chain, whether it's for cost or like the fee asset reasons or whatever, you have to, or historically you've had to understand and kind of make a judgment about this bridge risk that you're taking on different rollups. And if it's an L3, what guarantees are you taking on with like degen chain or whatever it is, and just like that is not a fair thing to ask an application developer, to have a perfect theoretical taxonomy of all of these different rollup frameworks and what the like matrix of risk trade-offs they're making is, and how to communicate that to their users. It's just like really complicated. We don't want to push our own global security model because we recognize that ultimately you need a security budget which scales with the value at risk, like we just discussed. Mm-hmm. And so it doesn't make sense to just like say, no, use ours. And so what we've done is we've abstracted away all of that chain-specific complexity as ISMs, such that our application developers have a very consistent and simple configuration interface. We will take on the responsibility of a default option, which we think makes sense for a majority of applications, especially who are just getting started. And if they reach a point where they're no longer, they have so much value at risk that they're basically, they can justify the security budget of an application-specific system like this, then we can move them off of, using the, native bridge of Arbitrum or Optimism to kind of like an economic security model, which is actually application-specific. Mm-hmm. But we basically have abstracted a bunch of these systems. We have a ISM, which is compatible with all orbit chains to move between L1s and L2s and L3s actually, L2 and L3. We have that for the OP stack. We have this for...
and how does that work at a high level?
So at a high level, the basic idea is we are wrapping the native bridges in the same API that we just looked at before of this message passing interface. So what we're like in these ISMs, we're actually just sending like the message ID from Hyperlane over the native bridges wire. So think of the like Arbitrum and OP stack native bridges as just like a black box that like somehow tells you that like a deposit or a withdrawal happened. We are depositing a message ID from Hyperlane, and we are getting that out on the L2 or vice versa. And we are then on the destination just basically like checking the message content from the relayer against this ID we're getting from the native bridge, and then proceeding with message processing. So if this works obviously between L1 and L2 and vice versa, but
it can be slow when it's L2 to L1.
Exactly, it can be slow when it's L2 to L1. And also, if you want to move between these, right, the kind of problem that no one seems to want to talk about is like, well, okay, if we need to go from here to here, right, we would have to, if I'm just on L2, if I'm an L2 user, like, the whole reason why I'm on L2 is because I don't want to incur L1 costs. Mm-hmm. But if we're only willing to take on the trust assumptions of these bridges, then the user will always incur L1 costs.
You have to go L2 down to L1, back to L2.
Exactly. And not only is that very expensive, but there's a 7-day window on this. So like we talked about earlier, the user experience of that is completely untenable. And so again, our solution to this is economic security, basically create a market for people to manage this risk and use validators to attest to this, right? Allow users to quickly move between these rollups. And yes, it's true that we are not taking on the most theoretically,
It's not 100%, but
there is some reorg risk, right? There's some, there's basically reorg risk, and we are ultimately counting on the insurance of the proof of stake system that is that these validators are opted into to insure users against that risk. And users are willing to pay a premium for that, right? Users pay for speed. This is like classic software stuff. So users are actually paying a fee on the hook. In addition to the fee they're paying to the relayer, they're paying a fee which gets basically apportioned out to validators.
Okay.
And that's like the insurance premium. But yeah, like there, I just listed the two probably like most well-known ones, but this list is increasingly becoming more diverse. There's like, more rollup frameworks that you can count on your hands, and like it's just
change as well.
exactly. And consensus models, and new VM architectures, and so like for application developers, they really just want a framework to be future-proof to all of this innovation that's happening kind of in the research community, but not enshrine some specific like global security model that will be like a vendor lock-in for them. And so really what this modular security system represents is an open source framework that kind of classically allows you to opt out of a specific vendor if you ever need to self-host in the future. Basically there's no vendor lock-in, and we are taking on the maintenance cost of all this stuff, right? So application developers really just have this very consistent message passing interface. They don't need to think so hard about these problems, which are really research problems that they shouldn't be exposed to. But yeah, that's kind of like the high level overview. You can, because these ISMs are smart contracts, in the same way that we were talking about composability, which like enable DeFi and protocols to borrow each other's liquidity, these ISMs can actually interact with each other. We have what we call aggregation ISMs, which
Calling multiple.
allow you to create like a tree of different requirements.
So like it has to satisfy this and like at least one of these or something.
Yeah, exactly. You can choose to have required and optional.
Which is super composable.
Exactly, very composable. Again, it's all in smart contracts, so like, you can literally go and like create your own ISM if we don't have it and just deploy it. There's no like permission you need from us for that. And our relayer understands how to encode the proof data for these ISMs to actually verify, basically.
So how would that work if there was like, let's say, a ZK ISM?
Yeah, so we actually have this available. We have wrapped the Altair, the Succinct Labs Altair Lake client, as well as we're working on their Blockstream X Lake client to get.
So the relayer would have to know how to create a proof.
Exactly. And there is actually ways for you in the ISM to kind of hook in or like tell the relayer basically to use some off-chain service. In the case of like Succinct, they have, or like a lot of these like ZK protocols now are building what they call prover networks that kind of have like their own APIs to fetch a proof for some circuit. And so you could think of like, the ZK ISM as basically like telling the relayer to go and fetch off-chain the Succinct proof to then pass to the ISM.
Or pass it as crossing the chains.
So
as the metadata.
Yeah. So the relayer is passing that in-call data to the mailbox when it's processing. And the reason why it's useful to have this is, again, different use cases justify different trade-offs in this kind of like matrix. And so we are actually planning to use this style of ISM, which trades off basically latency for safety, to secure the fraud proofs of some of these systems that we were just looking at. So imagine that we have the succinct blob streamx ISM from Celestia. All of the rollups which are settling to Celestia. We now have a kind of like, theoretically optimal view into what has been settled on those rollups. And we can hook that up to economic security, which is on Ethereum, and basically have validators attesting to rollups. Like basically it's similar to this, but just Celestia rollups instead of Ethereum ones. And we now get the cheap economic security from Ethereum, but the cheap DA from Celestia that these rollups are already benefiting from, and Hyperlane is basically providing economic security on that. And we use the ZK ISM to settle whether or not the validators have actually committed fraud. Because we don't, right? On Ethereum, we don't have a perfect view into Celestia. This effectively gives us that, right? This is effectively like a perfect view into Celestia, but it's expensive, right? So we don't want every message that is sent between Celestia rollups to incur that. But we do want this kind of guarantee on economic security. And so what we do is we move the cost and latency of this to the fraud proofs, away from users. And we basically lean on these validators to provide this fast user experience and take on that risk that ultimately can be slashed by this ZK/ISM
on Ethereum.
Exactly. But in expectation, this is not running for every message. And so we basically amortize the cost of actually proving, and obviously this part is also expensive, and that has its own kind of like cost structure.
So it allows you to verify that the message that was sent on Celestia, basically verify that on ETH.
Exactly, and then we get to the fraud proofs on ETH, and we're actually doing the same thing with Ethereum rollups. So if the validators are moving between Arbitrum and Optimism, right? We don't necessarily have a large proof of stake system available on Arbitrum, but we do have it on Ethereum.
Okay.
And so for this architecture, or for this topology, we can use the native bridge to settle the fraud proofs in the same way that we would for the blockstream X likeline. But we're only incurring that L2 to L1 latency and cost when there is fraud.
Okay.
Does that make sense? It's kind of quite complicated to illustrate. I think there's like a blog post that outlines this in better diagrams, but
yeah, it's interesting. Well, you're kind of detailing what's possible with all the composability.
Exactly, yeah. Like basically you can layer these ISMs on top of each other to get kind of like different guarantees where you move the risk and cost around between different parties. So like this style of thing that we're discussing is basically moving the risk and latency from users to validators.
Yeah, so let the validators settle the message in 2 seconds, but 7 days later they might lose a lot of funds.
Exactly, and allow them to create a market for that, like
And charge a
insurance.
fee for that.
Yeah.
So any closing thoughts?
Like if people are excited about this, definitely would love people to reach out or propose ISMs for their use case, or just come and collaborate. I want to emphasize that we are very much interested in reaching the kind of long tail of use cases for application developers, and part of that effort has been expanding to new VMs and new chains as they come live as fast as possible, to basically allow developers to leverage existing network effects like we discussed earlier. and be a future-proofing mechanism for apps. So if an application is looking to migrate, between chains or wants to, be on the latest and greatest chain, but doesn't really know how to go through that process, we definitely love to chat. We have in production the Cosmos VM, the C-level or Solana VM, and the EVM, where we're running a relayer. But we actually have the Cairo VM, the Move VM. We're working on the Ton blockchain. We have some folks working on Rootstock and some Bitcoin stuff. So definitely, again, really interested in the long tail. And we have a very vibrant developer community. Everything's open source. So we're looking for collaborators, basically, people within these ecosystems to come on board and kind of build this together. So yeah, definitely get in touch, and hope to see more people using Hyperlane soon.
Awesome, thank you.
So.